Hello everyone. Um, Today is lesson 3 of Solid Principles. It's a shorter lesson because we'll talk about a more simple principle called Liskov Substitution Principle. We'll talk about what it is, what is good code as specification, why is it hard to design clean inheritance, what is good inheritance, um, what solution parts do the least harm for inheritance, and the principle in other languages. So the best example about this principle, a classical example, is what happens when you look at a duck that is swimming in a pond. It quacks. It quacks quite nicely. What happens when you squeeze a duck that you have in your bathroom floating? Well, it quacks as well. So there is a funny illustration that sounds like this. If it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. A duck is an animal, however, a rubber duck is a toy. And when you think about it like this, you realize that it's two different things. So they can't be the same thing. The formal definition of this principle says, any class that is the child of a parent class should be usable in place of its parent without any unexpected behavior. It's quite complex to understand, but if we break it down, we realize that uh, basically a child should be replaceable by the parent, and that shouldn't cause any problems. And the simplified version of LSP, Liskov Substitution Principle, is simply don't fake it. Rubber duck is not a duck. That's the initial problem of the whole thing. So if you have a class and if you do apply inheritance, or if you implement an interface just to conform to a contract, but not really to the specification that is underlying, in other words, being just semantical and not very logical, you're faking it. So don't fake it. That's the essence of this substitution principle. And LSP targets not only inheritance, but it targets whatever provides subtyping, so interfaces as well. Now let's talk about how you should create subtypes in a good way. Good subtypes are logical. So you should enforce business rules through logical relations between classes and interfaces and nothing else. Reusing code, or again, semantically implementing an interface or semantically reusing something, doesn't make sense. And examples of that is cat and dog are animals, right? So that is logical. Rubber duck is a toy, that is logical. Team is not a list of players, that is true. Team has a list of players. So other than being logical and keeping the same semantics, it needs to also keep the same specification. What I mean by this, that if let's say the parent class would throw a null reference exception, then the child class should also have the possibility of throwing null reference exception. Regarding the thing about team has a list of players, what we learned under composition, that is a good remark. Um, Open-close principle, and in general, all principles of solid are interrelated. They're very similar to one another. For example, single responsibility principle, in order to implement it well, you need to conform to open-close principle. To implement open-close principle well, you need to conform to Liskov substitution principle. In order to implement Liskov substitution principle, you need to conform to both interface segregation principle and dependency inversion principle, and so on and so forth. So they're all very related principles, really. And it's hard to talk about them in isolation. Therefore, some traits that you see now are the traits that you saw also from the previous lesson. So specification intact means that a child class should not throw any extra exceptions, because that's not what the specification was before. If it was throwing null reference exception, it should be throwing null reference exception. A bad example of this would be, imagine a calculator that works with both negative and positive numbers, and then imagine you suddenly make a subclass of that calculator calling it negative numbers calculator for whatever reason. And you pass a positive number and it throws an exception. Well, you just broke the contract. The specification initially said that you can work with all numbers, but if your child works with specific numbers, you're breaking the contract. The specification was not like that before. And expanding on this, in C#, compiler cannot enforce that. In Java, you can specify and inherit the contract that says what exceptions methods throw. The contract, the base class or the interface, they're supposed to be stable. A contract is something that you settle with and try not to change. Because if a contract changes, the consumers will have to adapt to that change. So every time a contract changes, it's more or less a breaking change. And therefore you should be very careful and think very well and think twice before creating an interface or a base class and inherit it. Because it's a breaking change if it changes. This applies to other things as well, of course, when you're consuming things, but now we're just specifying it in subtyping. Regarding inheritance, as we said, if we override behavior incorrectly by having behavior that suddenly does things that it shouldn't do, like has extra validation that was not in the initial contract, it breaks the specification. So rather than overriding stuff in inheritance, we should focus on adding new things. So incremental inheritance, if we manage to design it like that, is all right. Incremental means that we also work with it in isolation. In isolation means a child should not refer to a parent, because parent and child are already coupled between each other, and if you add an extra coupling between them, that just makes things worse. It will be harder in the future to refactor if you suddenly have child that refers to parent. It is a strong relation, and that relation just became stronger. And of course, with inheritance, if we're looking at the class that actually carries the implementation in a child, we go deeper and deeper and deeper. And if it's one level deep inheritance, that's already two classes that we had to visit in order to find the implementation. So it's hard to navigate code that is deep, and the equivalent of this is nesting. So just like we don't want nested if statements, nested loops. We don't want nested inheritance, deep inheritance as well. It's complexity that should be avoided. So one level deep inheritance is okay. More than that is something that you should avoid. And that being said, inheritance is hard. Inheritance is hard because, well, as I already said, it creates coupling between parent and child. It creates coupling because there is no way of escaping the details of implementation that come with inheritance. And if a child or parent changes its contract, it changes two places at least. So a change there is a breaking change because the implementation needs to adapt to the contract. And therefore it's hard to design. And therefore we prefer composition over inheritance, again, as we mentioned in the last lesson. Before I go to Smel's part, which is very small, I'd like to mention also languages such as PHP. PHP is a dynamic language, meaning which it will only ever throw an error on runtime. There is no compilation, so if you did something wrong until the code hits the place, you won't see the error. And in PHP and the alike, you can also mess code in such a way that, for example, a function has no return type. If you just write the function, that means that it can return something, it might not return something, and it will fail or work, but you will understand it only after running the code. So for languages like PHP, Liskov's substitution principle also means semantically that if a function, if an interface required you, or if a base class required you to return something, then in a child class you should return something that the base class required. Even though technically that would work, logically it's a horrible idea and should be avoided in languages like that. And regarding code smells, this is really just the same thing that I already said differently, and this is Liskov's substitution principle violation said differently. And basically a symptom. If a subclass uses only some of the methods and properties inherent from its parents, the hierarchy is broken. The unneeded methods may simply go unused or be redefined and give off exceptions. For example, we have a car and a broken car. Well, we might think that a broken car is a car, but a broken car cannot move. So that fundamentally breaks the logical meaning of a car, like a means to move, transportation. So if we cannot do transportation, we shouldn't say that a broken car is a car. So such contract violation is this code smell, and the hidden meaning in the name is that things aren't what they seem to be. And therefore, when you are interacting with those things, like with a broken car, and you say, go, move, it simply throws an exception. A broken car cannot move exception. In other cases, so a broken car shares the body with the car. Sure, it's bent, broken, maybe lacks some parts, but in essence, it's the same body. So a broken car has the body. That's about it, probably. However, a car has a body, has wheels, engines, and it all can move and work together. And it can move. So the components that are responsible for moving and the components that are responsible for just visually maintaining a shape of a car should be separated, and the remedy to refuse bequest code smell is to simply split a class to just parts that we need and refer to those parts instead of a massive base class. Now let's try to go to Visual Studio and make some code examples. But before I go there, let me ask if you have any questions regarding this topic. Also, hello, Walker Recho. Okay. I've bumped into situations like the one you just mentioned about the cars, so was it a good idea to not inherit from the base same class, instead just use their own? Yes. In cases like that, definitely. If you stumble into something that isn't logically what you try to use, and the symptoms is that it has not implemented exception, or it behaves completely different than the parent, then that's a violation, a severe violation of Liskov's substitution principle. And I'll show a bunch of examples that illustrates the point. So the first example that I'd like to show will be about ellipse, rectangle, subtle violation. Okay, first let's make a car violation, severe violation. Okay, let's make that example with a car. Let's delete this one. So we have a car. A car has what? It has an engine. So private, read-only. I'll just call it dynamic because we really don't care about the parts themselves. It's just an illustration. It has wheels. What else does a car have? Body. So that's our car. And what can we do with a car? We can start the car, you know, so it hits the engine. What does the engine do? Run, let's say. And we can also move to a location. So a car also has a location. Which is public this time. So a car has a location that we know of. So we can get and set it. So when it moves to some location, it moves it like this. It interpolates the location, doesn't move there immediately. What else does a car have? A car has a speed, a color, though that's more a property of body, so I won't mention it. So a car has speed, and probably a car has what's it called? I don't know the English word for it. Kilometers traveled. well, we don't want to set it privately. Okay. So when a car moves, you know, it says, well, distance between its location and location that it travels. And let's say that's in kilometers. So we say that km traveled becomes distance between the two. And we set the location. Okay. So that's our car. Okay. And as I said, we suddenly have a need of a different kind of car, a broken car. And we say that a broken car is, well, a car. What's the problem with this? Well, the problem with this, let's implement it. It might have wheels, engine, and body as well. Dynamic arguments. Let's just have a bunch of empty classes, let's say. Okay. Great. Car, engine, everything needs to be public. Great. Engine, wheel, body. It might have, it might not. It really, if a broken car doesn't have any wheels, I'll just say it's null. But that's a good point. Like, it doesn't have to have wheels, nor engine, nor other things. The contract, so the first contract, how we build a car, we explicitly ask that every car has to have engine, wheels, and body. So the first violation without doing anything is here, as you said. A broken car doesn't have to have those parts. So violation number 1 is a broken car doesn't have to have all those parts. It's broken, duh. Okay? Next. Violation 2. There is no point for getting speed or kilometers traveled. For kilometers traveled, maybe there is a point, like we might know how long what was the journey that it went. So, but essentially, speed of a car. The speed of a car. Actually, the speed of a car should have been here as well. Whoops. It's not what I wanted. Add argument. Come on. Float, speed. Speed. Again, makes no point. So that's the second violation. The third violation is actually the fact that it can move. A broken car can no longer move. So these are the three violations that a broken car has. How do we fix it? Let me move this. So a good broken car will not inherit. And I'll just go to a car, and for now I'll just copy it. And okay, location is needed, this is not needed, this is needed. These three are needed, but they are, well, probably they're not needed. For now, I don't care. So I don't care about this. Kilometers traveled is not going to be set anymore. It's just going to be got. Engine is not going to be started. And basically, that's the broken car. It has absolutely no meaning. It's just there. We know where it is and we know when it broke. Rather than, well, how many kilometers it traveled. That's all that we know. That we need to know about the car. So let me add the final touches. That's it. That's the car. And location doesn't need to change, so it's a getter only, because it's broken. It's there. It's not going to move anywhere. Yeah. And logically, you try to interact with a broken car. Like, imagine if you go to a car shop, to a dealer, and he says, well, this is a broken car. And then he starts talking about a normal car that can reach this kind of speed, has this kind of engine, and travels fast, and it's just great, and so on. But the broken car doesn't do that, so what's the point of knowing all that? I just want some scrap, man. Just give me some scrap. Not a car that is not working. Well, not a car. Don't talk about a car if I don't need a car. I just need scrap. I just need some debris. That's debris. And if I inherited it like this, debris which has a location, let's say, or even better to say that we have an interface called iLocatable, and we have a location. So that would do. I can do that with a broken car, with a car. So I can add this to a car as well. So basically, now if we look at this, the only thing that's common between a car and a broken car is that we can locate it, that it has a certain location that we can get publicly. That's the only common thing. Just because it is a car visually doesn't mean that it is a car functionally. So when we think about inheritance, we shouldn't share common structure, we shouldn't share semantics, we should share logical behavior. Yeah, I can definitely do that, and in a normal project that would be done. So let's right click on a car. And let's extract interface for moving and say that it's iMovable. And we can go as far as saying that all cars can move and can be located. So this interface also applies to Liskov's substitution principle. We have an interface that's composed of other two interfaces, though this is more about next lesson topic, but I just showed that this can be done. So what is a car? A car is something that can move and that we can locate. That's a car. So our car is this. Clean, simple, neat, not cluttered, and nothing extra that we need to do. All right. So that is the first example about severe, obvious violation of Liskov's substitution principle. Now let's go to some other example. Imagine that you have a square and a rectangle. And mathematically, if you define the two, you will notice that they are quite similar, right? So let's try to make that. A rectangle. So a rectangle has public, float, width, public, float, height. Bad, good. And now we just do this. That's it. Maybe we have space, public, float, more like here. So public, float, area. What's the area of a rectangle? It's width times height. Okay. And imagine we have a square. And the square is a rectangle mathematically, isn't it? So that's kind of logically true. Like, no new behavior we introduce, everything is the same, and, well, things would be quite alright for what's the side. Let's call it side. So when we create a square, we just pass width and height is the same, so it just implements it that way, right? So we have a square that is a rectangle, and a square just has a side, and we don't care about width and height. We just know that there is one side. 4 equal sides is what square is. If you look at this example, could you tell me what's wrong? Square. So we just created a square which has both sides, and then we say rectangle has height rectangle has width, and rectangle has area. Hello, thanks for wait. I'm just talking about Hello. I'm just talking about the example of Liskov substitution principle violation. So maybe you can uh, answer and help Dave with the question. If we have a rectangle, which is a very simple class, a rectangle has a width, height, area, very simple. And then we have a square. Well, a square is a kind of rectangle, which is mathematically true. So all four sides are equal, so there is no point passing width and height. So I just pass a side, and I create a rectangle like that. Everything remains the same. All is good. All is good except one thing. What's wrong? What's wrong with this kind of square implementation? Can anyone answer? Yeah, it is a violation because you're using two variables. So when I'm printing information about as a rectangle, I use both width and height. When I'm printing information about a square, I'm starting to be confused. Should I be printing both? Should I be choosing height or should I be choosing width? And the biggest problem with this example is not that we have both of them, is that both of those are actually mutable. Even though this is a square, I can still set its other side to 6 or something like that. So violation number 1. Well, I'll put violation number 1. We have more than we need. Only one side is needed. And violation number 2. Is that if a rectangle was mutable, square is mutable too, so we can change one side without changing the other, making it a potential rectangle. Yeah, if I do this, the below is no longer a square. So this, even though mathematically this is true, programmatically this doesn't really conform to solid principles. It fails at L. Now, a better example of this would be what's the easiest way to fix this? To keep all squares. What would be the easiest way to fix it? Sure, that would be the most correct, but if I choose to inherit, well, interface would be better than abstract class. There's nothing abstract about those two, and why is it two duplicate classes? I don't get it. There's something else we can do. Obviously, inheritance is a bad choice here altogether, but there is something else you can do. Shape is also fine, but again, What are we using from shape? Area? Sure, but there's something else. Something interesting. One more little thing that we're missing a bit. How can I enforce? What change should I do in order to prevent breaking things of square? What is the breaking thing of square? The breaking thing of square is the mutability of a rectangle. So instead of overriding the setter, I should simply make it immutable. If I cannot set width and height, then by creating a square, after I created a square, I will no longer be able to break it. So even though this violates the Liskov substitution principle, it's not as severe as before, because logically it's still it will always still keep the square properties. The only downside is that you're slightly, having height and width, but it's not a big deal. It's not a big deal because, well, sometimes, you talk about square as something that has both sides that are equal, which isn't anything that is broken, it's just slightly excessive. But just because of that, it's not broken and it cannot break. So it's a kind of fix. Obviously, the best thing to do would be to simply avoid inheritance altogether, because it's quite trivial. But for this example, this kind of thing is also fine. And I'll show you a funny thing as well. When you look at the .NET framework, you often picture it as the ultimate source of the best design ever. But they are not perfect as well, and they're the same human as us, and they make mistakes too. So I'll try to show one mistake in design that .NET Framework has, which regards in iCollection implementation. So we have a static class that will serve as means of running a demo. And what are we going to do? I'll say iCollection of string will be new string array of 10. And I'll say collection add hello. And let's try to run that. So .NET framework run. And as you can see, it says not supported operation. Collection was of a fixed size. So even if it was not supported, .NET Framework still allows us to do that. So array is not actually supposed to implement the contract of iCollection, because we cannot add elements to it. And as a workaround, .NET Framework has property, is read-only. So if I say if is read-only, I can then add it. So they do have workarounds, but this by itself is a big violation of Liskov's substitution principle and the framework design, and they shouldn't have done it this way. I'm not sure why they did it like that. I really don't understand. But that's the choice they made. Regarding violation of L, there are many examples. What do you mean no lowering behind that syntax? And well, I'd say that inheritance altogether is a thing more of the past, because you'll see a ton of books that back in the days would write about inheritance being key to so many patterns and solutions. But nowadays it's more about immutable state, composition, and things like that. So Workarounds said, is there no lowering behind the syntax? Like the syntax is changed in order to make it work? Well, there are workarounds, and I think just by being burned from this, by doing this by accident, you'll understand that that's not the way to do it. But this is a flaw in design of language. It shouldn't be designed this way in the first place. Well, I just ran it if you didn't notice, and it was breaking because collection is read-only. You see it throws this exception. Not supported operation exception, collection was of a fixed size, which makes sense, but again, it's basically it's the same. It's really a classical violation of LSP. It's the same as, you just have I full. Well, I'll say I collection, literally the same thing. Void add. Item. And that's all. And then I'll say which is I collection 1D, and let's implement it. Boom, amazing implementation. And the other one, I'll say that it has a private read-only list. Add item. Okay. And what else am I missing? I don't want that. Create a new list. Actually, just initialize it here. Okay. 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 More like not supported exception. Need to fix interface. Yes. Okay. And what did it say? It said collection is of fixed size. It's fine. Array collection, list collection. Extra on line 14. Probably a bit late. Yeah. Okay. So let's comment this out. We don't care. So array collection, list collection first. For string, and we add it. We say that it's I collection 1, and we add hello, and we do the same with another collection. Okay, and we add hello as well, and sure, let it be like that. Okay, let's can indexer be it's out of scope, I won't write it. Yes. So now we just basically simulated what .NET Framework did. In their case, obviously way more methods, way more complexity, but the idea is the same. Yeah. Now you might wonder, when should you actually use inheritance, and does it have any purpose in modern programming? And the answer is it does, and it works, but there are probably always better alternatives. And I really tried to play devil's advocate discussing this with my colleagues today. How does inheritance help in, let's say, Windows Forms application, where you can define a base form, inherit it. But guess what? I defined the base form and I inherited, and it broke the designer. So it caused problems. I probably was doing it somehow wrong, but that's besides the point. By simply having my own custom components and compose a form out of those components, rather than trying to inherit the form, would probably be a better solution. Basically, having a template or a themed set of controls is, again, a composition-based approach versus inheritance-based approach. ASP.NET, again, if we look at the design the framework gives us, it often focuses on something that you can work with rapidly. I don't have example at the ready now how to make it better, but when we work with ASP.NET Core and we create Web API, we always inherit controller or base controller. And I was shocked today when I heard that there are people who don't do that, who write their own controllers and compose them out of things they need. So they lose all that noise that comes from the framework. Even a controller, something as what I used to think infrastructurally complex, can be made simple and conform to solid principles. Because right now it does not. It has more things than we need, just in case. So they tried to remove the complexity, but it has its own set of problems. With inheritance and a lot of moving pieces that we don't need, we increase the risk of breaking things quite a bit. So is that worth the cost that it takes us to learn to use it properly, rather than using it fast but having issues long term? The answer to that is probably that we should start learning how to work with things properly and not just go for the quick and dirty solution. And not just be happy about what framework gives us. We should have our own mind and think logically. So to sum this up, I'd like to say that don't use interfaces and inheritance for semantics. Just because a contract requires you to do so, don't do so. Do so because it logically makes sense. A contract is specification, so keep to that specification. Because if contract doesn't conform to a specification that you required, you will start doubting the code base that you're consuming. Trust the code base, and that trust can be only secured through conforming to Liskov substitution principle. That is it for this lesson. I would appreciate if you could write one thing that you think you understood very well, just a highlight of the lesson, and one thing that maybe you're curious about and would like to understand a bit better. I'll be right back. 1 minute. All right, let's see. Um, Okay, really good simple example of square 2. I'm out. Okay, see you guys. Well, I joined late, but I figured out what we were saying about the square problem. See you all. Bye-bye. All right. Yeah. I hope, well, to summarize, for those who were late, in a nutshell, Liskov's substitution principle simply says, don't fake it. Don't fake it. Keep it true. Conform. Don't use inheritance as means of reusing code. Don't use inheritance or interfaces for semantical stuff. Just whatever syntax conforms or whatever causes you to write less code. Use it to create your domain rules, to enforce business logic and make strong relations between things that should have those relations. So Liskov substitution principle says that you should be able to substitute your super base class with a more derived one that inherits it without breaking other parts. Exactly. That's what it says. Right. So thank you all for watching and see you on Saturday, where we'll talk about interface segregation principle. Bye bye.